greatest scientist in physics, he found out that the white light is not just white. It consists of 7 colors. So the rainbow that you see is coming from the this idea. So the white light, he noticed that from one of his windows in his lab, he noticed that the white light comes in through the hole in the door, and it's lighted onto a prism, which is a rectangular shape device like this. It is 3-dimensional device. When the light enter into that device, it's created the rainbow colors on the screen or on the other wall. Maybe you have noticed this in bicycles, like in the bicycle, there's a little piece just rotating with the wheel. It will reflect the light and create the rainbow colors. Maybe you have seen it. And also your wristwatches, like these glass pieces, sometimes scatter and create these color lights, right? So anyway, so the white light consists of 7 colors. So we can split this white light into these different colors by using a prism. All right, so if you remember, we learned about electromagnetic wave. So the visible light is within that electromagnetic spectrum. So light is an electromagnetic wave where you can see the electric field and the magnetic field are vibrating in perpendicular to each other, right? So visible lights come from red color all the way to violet. This diagram should be edited. It's going from red to violet. Anyway, these numbers are correct. So it's starting from around 700 nanometers, little more than that, like 750 something, and then go all the way up to about 400 nanometers. So I would say about 700 to about 400 nanometers. That is the visible spectrum wavelength. So starting from red to blue. So we say like red color that has a long wavelength but shorter frequency. Then the shorter wavelength, which is blue color, and it is a high frequency. So in researchers, we say like it's blue shifted or red shifted, depending on which side it's moving into. It's like short wavelength or a long wavelength. So again, white light is a mixture of all visible wavelength. Rainbow is an example. So you see like all the 7 colors are getting distributed by using just the white light. And nanometer, so again, I'm using a different unit here, nanometers. It's lowercase n and lowercase m that represent another unit to measure the distances. So when we need to measure tiny distances, we use different units like nanometers, micrometers, right? Picometers. So this nanometer means it's 10 to the power minus 9 meters. So basically it's 1 divided by 1 and 9 zeros. So it's 0.000000001. Okay, that is a nanometer. So in meters, it will be 10 to the power minus 9 meters. So if you see 400 nanometers, that means 400 times 10 to the power minus 9 meters. So nanometer means a very tiny distance that we cannot read from our eye without any aid, but we can see these colors, right? All right, so why is the sky blue in the daytime? We see this blue sky, right? So if we go for a quantum mechanical explanation, it is heavy, but we don't go for in that detail, but roughly let's see why do we see a blue sky in the daytime. Now we learned that the blue light has a shorter wavelength, but high frequency, right? And the red light has a high wavelength, but a small frequency. So when the like sun is in the sky and it's emitting white light, which consists of all the 7 colors, and it's entering into our atmosphere. So when it's entering into the atmosphere, this light waves try to scatter around in each particle. Scatter means it's bumping out, right? So it's get bumped into the atmospheric particle, oxygen, nitrogen, hydrogen, helium, whatever it is, it gets scattered from that atmospheric particles. It can be dust particles. So any particle that in the atmosphere, the light gets scattered. So blue light is scattering fast than the red light. So in the daytime, the sun is overhead to us or the high in the sky. So when the sunlight scattered into the atmospheric particle, the blue light are the fuzzy guys that they are scattering really, really fast and reaching to our eye before the red light does that. So we see the blue sky. So there's a little delay. So red light is coming, but blue always overcome the speed and it reaches to our eye faster than the red light. So we see this red light in the sky. We call this theory as a Rayleigh's theory, but we are not going to learn that. It's come with a lot of mathematics in there, but if we want, we can explain that. But roughly remember, like, why do we see a red blue sky in the daytime? It's because of the scattering speed of each wavelength. So blue light always scatter faster than the red light. So we see the blue color before the red color. So that's why we see the blue sky in the daytime. Now, why the sunset and sunrise are red or yellowish color, right? So I believe you have seen the sunrise and sunset. So at that time, we see all the clouds and everything in that region is reddish, yellowish, orangish color, right? So why? Again, I think you can explain that. So if you look at the distance from the sun to the atmospheric over here, there's a fly around in my room. Sorry. Okay, so when the sun is in the below the horizon, like somewhere here, then the sun rays is coming, again, they are scattering, right? And when the sun is far, like in the horizon area, then there's a little longer distance that sun rays should travel before it's come to our eye. So again, the blue light are really fuzzy, so they are scattering fast, and they lose their energy really quickly than the red light. So red light scatters slowly, but as it is moving slowly, it can save its energy until it reaches to our eye. So when the sun rays come from sun, enter into the atmosphere. So once it's entered the atmosphere, it gets scattered. So the blue light gets scattered and it's lose its all energy before it reaches to our eye. But the red light or the orange yellow colors, they are scattering slower than the blue color, so they can save energy and it will reach us to our eye. So here blue light is not surviving until it's come to our eye. So the red light does. So that's why we see red color in the sky at the sunrise and sunset. Daytime, it's different. It's not compared to the sunrise and sunset times, the sun rays are traveling shorter distance than the other two places. So blue will reach to our eye faster than the red light. Okay, now the visible spectrum, which is white light, so it comes with all the 7 colors in our rainbow, but we don't see all these colors separately, right? However, all these 7 colors in the visible spectrum, our eye is sensitive differently for each color. So you see here, this diagram, the graph shows the sensitivity of our eye into daylight. It is white light, but see our sensitivity, we really like this green, yellow color, right? So that is the highest sensitive percentage. But red color is all the way down here. So our eye is not that sensitive to red light. So the green, yellow color is our preferred sensitive region. That's why we do like this greenish color, right? So always greenish color make comfortable in our eye than red color. Red color always hurts our eye, right? So because this is the reason. So we are not that sensitive to this red color. All right, so let's assume that we have light sources with the same intensity. Intensity means how powerful they are. So let's say I naught. So then let's say one source is emitting 450 nanometers and the second one emits 550 nanometers and then third one emits 650 nanometers. So which of these sources will be most intense when detected by our eye? 450 nanometers, right? So where's 450? It's somewhere here. Read this scale. This horizontal scale reads the nanometers, that's the wavelength. So 450 is somewhere here. And then 550, that's somewhere there. So it's greenish, right? And 650, it's somewhere there in the reddish, right? So they're emitting the same intensity, but our eye is high sensitive for this region. So anything in this region from 500 to 600, let's say, that is green, yellow color. So that is the region that we will be more sensitive. So the light source that emit 550 nanometers will be creating high intensity in our eye because we are high sensitive to these light rays. All right, so if you look at this color, which one hurts your eye and which one kind of feel good here? Red is, we feel like red is bright, right? Red bright, than the green, but we prefer to go to this one. So green always catch our eye before the red. Red hurts our eye. All right, so color mixing. In your art class, if you mix all these 7 colors, will it give white color? I believe you draw pictures, you use your watercolors in when you are in kindergarten or in the elementary schools, right? So remember, like if you mix everything, it will make black. But interestingly, when you go to the electromagnetic spectrum, all these 7 colors, when you mix those 7 colors, it's produce white light, right? Anyway, so when the color mixing, like if you're doing printing, so in the printer we are using 3 color tones to create the any other color. So if you look at the toner, the color toner, it comes with only 3 colors in there, but it's mixed up and create all the other colors that we need. So when the the pigments that used in paints or dyes work by selective color mixing. So let's say I'm seeing a any color, like let's say yellow. So I'm seeing yellow color. So why do I see this in yellow? What happened to other 7 colors? It's not there, right? So this yellow color is the only thing that my eye catch. So that's why I see this yellow color. If I see red color, that means this only emits red color. Now, this is not a light source. It is just a paper, right? So it is not producing light. So this paper is using the white light that available in the room. So that is sunlight. So sunlight, which is white light, hit on the surface of this yellow color surface, and then it is 7 colors. All the other colors get absorbed, but the yellow color is only scattered out and reach to my eye. That's why I see this in yellow color. Now I see black color, right? So all the colors get absorbed, and it's not all the colors, but it will save some colors, and it's mixed up and it's emit only the black color. Now here I have a blue color card. So I see blue, that because all the other 6 colors get absorbed, only the blue color gets scattered. Only blue color survived, scatter into my eye, so I can read the blue color. So when light strikes an object, some of the light undergoes specular reflection. So I call this as a scattering, but it's really, we call this as the reflection. It hits on a surface and reflect back to my eye. So like in this picture, so these all 3 colors hits on the surface and reflect into the eye. So we can see all these 3 colors, but we don't see separately blue, green, red, but a mixture of colors. So it's mixed up and we'll see a different color in our eye. Then any other color that hits there, it will get absorbed. Now surfaces, like this surface is not smooth as in this picture. It's maybe it's just bumpy, and the light can enter into the surface and go depth into the material. It still doesn't matter. The light will get reflected, but there's a law that follow by these lights when they are reflecting. So let's see what it is. And these are color mixing. So in the printer, we don't see red, yellow, green, but instead we are using magenta, cyan, and yellow. So these are the 3 colors that we are using in the as pigments in the printer toner. So all these 3 colors mixed up, and it can create all the other colors. So depending on which portion you are mixing, it will create different colors. So in the art class, maybe you have learned like 3 basic colors are yellow, green, and what? Blue? Yeah, yellow, green, and red. I forgot. Yellow, blue, and red. So in the art class, we use yellow, blue, and red to create all the other colors, right? In the printing, we are not using red, blue, and yellow. Instead, we are using magenta, cyan, and yellow. So these are the 3 colors that we are using in pigments in the printing ink. Okay, so that's all. Now, image formation, that is a very important piece about light, because light is there and we see these different cards, cups, and some are transparent, some are solid. So there's a reason for it. So let's see how these light create images, and how do we catch that, and what are the application of this formation. Now, maybe you have heard that light is behaving in two different ways. One is it's behave like a wave, and it behaves like a particle. I think we talked about it last time, but not in detail. I will go in detail about the dual nature of this light later. But for now, let's think that the light is a wave and it comes like from the sun to our eye, and it's let's say it's come to this cup, it hits on the cup and then reflect into our eye, and then I catch it and it's create images in our brain, right? So that's how we read it. So when you modeling these waves or the light, we use the ray model. So ray model means it is a wave, right? So there should be a sine curve, as we discussed the last time about the waves. But here we are not going to draw these waves to represent the light. Instead we are using rays. Those are just like these lines. So we are using this arrows to represent the light rays. We call this as light rays, and this is the pointer describe the direction of this light rays. So light rays are starting from this side and travels to this way. So this represent the light rays. Now wave fonts, those are the, like if you draw the real wave, it is like a sine curve. So all the troughs will be in this region. So we draw the perpendicular line to the wave fronts, and then light ray is parallel to the wave propagation direction. So basically we are not going to draw wave lines, but we draw these straight lines like arrow lines to represent the light rays. Okay, what is it? Did anyone send me a chat message? Is it something important? I don't have access to it for some reason. All right, so you can unmute and tell me if it is a very important one. I saw that I got a chat message, but it's gone from my side. All right, so the law of reflection. So, you know, like I mentioned that when the sun rays come from the sun and it's into the atmosphere, and then if you are seeing an object, the light rays hits on this surface and it's reflecting into my eye. And this light is following a rule when reflecting these lights. So we call this as the law of reflection of light. All right, so here we have a surface in this picture. Try to understand the picture. So on the bottom, we have this surface, and this is the incident light. So again, we are using ray diagram here. I'm not going to draw waves. I draw this straight line. So this is the incident ray, and it hits on the surface and it gets reflected. Now you will say like, oh, light is absorbing. There's one, a limited portion is absorbing, but we are going to pay attention to reflection. So the light hits on the surface and 70% of the light get reflected. Okay, we'll talk about what happened to the 30% later, but for now, here the incident ray, 70% of the light get reflected. Now, if you draw a perpendicular line to the surface at this point of contact, then let's measure this angle, the angle between this perpendicular line and the incident ray. And then that is the angle of incident. This is the angle of incident. And then the angle between the reflected ray and the perpendicular line here, that is the angle of reflection. These two angles are equal. It's amazing. It's happening in the nature. So when the light hits the surface, it gets reflected, but it's always create these two angles equal to each other. Okay, so angle of incident is the angle between this perpendicular line and the incident ray. It is not the other one. It's not the angle between the surface and the incident ray. Angle of incident is the angle between the incident ray and the perpendicular line. Here, this is the reflected ray, and this is the angle between this the perpendicular line and the reflected ray. If you were in the class, I'll give you some the laser light and a reflected beam so we can actually measure it. Here, incident ray and the reflected ray, this incident angle is equal to the reflected angle here. That is what's happening in the mirror. So when you look at your face from the bathroom mirror, that means the light rays that's coming from the light in the room will hits your face, and that light get reflected to the mirror, and the mirror is creating that image in there by using that reflected light. And the light that hits our face, it's reflected following this law. Let's create the incident angle equal to the reflected angle. Okay, so there are different types of mirrors. Plane mirror, that is the mirror in our bathroom. So plane mirror, it's something that we can use to see ourselves. It's create the same size mirror image and in with the same distance. So if you look at from the mirror, you see yourself like exact same size and then in the same distance. Like if you are closer to the mirror, the image is coming closer to you. If you go away from the mirror, then the image also going away from the mirror, right? It is inside. So it is a virtual image that's created inside the mirror. So it's behind the mirror, not in the front, it's behind the mirror, but we can touch it, right? We cannot touch our image. So we call this as a virtual image. Nice thing about plane mirrors is it's creating the same size, but it switches the direction. So when we say mirror image, that means it switches this our direction. So if you want to touch your eye, you think like, oh, I'm touching here, but you're really touching somewhere else when you see the mirror. Like when you're looking at the mirror and if you trying to touch left, you're actually touching the right side. So it's mirror imaging, it's switching the directions, but it's create the same size and same distance. Then the concave mirrors, it's something like this way, like it's curved into inside. So when the light rays comes in, it can collected into one place. So these are concave mirrors. If you do solar cooking, we are using this mirror, and in telescopes, we are using these mirrors. And then convex mirrors, it's flipped around, like it's bended in the opposite way, like this. Concave, it's caved, it's creating a cave here. Convex is the opposite, so it's bended like this surface. So convex mirrors, we are using these convex mirrors in different places as well, especially like where do we use convex mirrors? If you want to scatter like spread around, like for many places, like just oh, in the vehicles we are using those
Car mirrors?
say it again.
Convex mirror
Yeah.
are example for car mirrors.
Yeah, in car mirrors, we use convex mirrors in some places. Let's look at, I think I listed down some applications. Suddenly I don't get it into my mind. All right, so this is what happening. So when you have a curved mirror, the light hits this curved mirror, but it's follow the reflection law, that it's creating the incident angle equal to the reflection angle, and it's just kind of bending the light, right? So we are using these mirrors to bend light differently, and it's sent into the same direction as the light came in. It's not going into the mirror, it's reflected back into where it came from, right? But due to this reflection angle, the reflection angle from this caved surface, the light can connect into one place. So we call this as the focal point. This is the focal point because the light rays get reflected and collected. I think you're following my animation here. So that when the light hits the mirror, it's get bended and it's collected, like all the lights are collecting into one point. So these are we call this position as the focal point. And the focal point is in the same direction where where the light rays came in. So this side is the light came in, and the focal point is in the same direction. It's not behind the mirror, it's there, right? Okay, so advantages of mirror for focusing light. So all wavelength reflect the same way. So every wavelength follow the reflection law, which is creating the equal angle, like incident angle is equal to the reflection angle, all the wavelengths. So it doesn't matter whether it is red, blue, whatever the color it is, it's reflect. So we can use all the wavelengths to reflect, and there's no chromatic aberration. Chromatic aberration is a something that happens due to the wavelength differences, like when you have different shape of lenses, it's about lenses. So there's no chromatic aberration when we are using the reflection. So reflection, it's happened for all the wavelengths. There's no difference in that. Chromatic aberration is the light is behaving for differently for different wavelengths. So there's no chromatic aberration in the reflection. So only one surface is needed to do the reflection. So mirrors, it's just there's only one surface and the light get reflected and it's create images. So mirrors can be up to 5 meters in diameter before the weight become a problem. right? So we can go up to about 5 meters in size. But still there are so many large mirrors that we are using in different places, like especially in astronomy. In China, they have the largest array of these cave-shaped mirrors that they're using to detect these light rays that's coming from outer space, right? And its computer controlled diameters are there as well. So flexible mirrors, like you can change the size of the mirror and program it by and change the shape, and also they can change the size. So this is an example of telescopes that they're using these mirrors. Subaru telescope, which is 8.2 meters telescope, and it is a National Astronomical Observatory of Japan that's located in Hawaii. It's a Japan owned telescope, but it is located in the observatory in Hawaii, Mauna Kea. Right? So this is a picture of that telescope. They're using mirrors, and the light rays are coming from high sky, and it gets reflected from the mirrors inside the telescope. And here's a mirror in our car. That's a convex mirror. That's what I mentioned. So this is the convex mirror in your side mirrors. So when you look at the mirror, you see small pictures of something behind you, right? So this is a convex mirror. But objects, like if you look at this picture, here's the object means whatever the thing that you're seeing in the behind, like let's say a tree. There's a big tree behind the car. So this is the object, that means this is the tree, and the light rays that emitted by the object. Here in the diagrams we are using only couple of light rays, but you know, like whole body of the tree is emitting reflecting light rays that's in the surrounding. So the light rays that's coming from the object will hit on the convex mirror, and it's create an image behind the mirror here, because this is convex mirror. And any mirror, we see the mirror image is behind the mirror. Here we have this virtual means it's not real, it's virtual, and upright image. So here's the image. It is in the same side, like all the trees are upright, it's not upside down, we see the same direction, but it is small. So when you're looking through the mirror, you see these trees look small, right, than its actual size. So using convex mirrors, we create virtual, upright, but small images. That is why we are using these convex mirrors in our side mirrors in our vehicles. So we can see a larger area which is behind you, right? So we have the mirrors in front of us, but we see something in behind on the screen. It is virtual, so this the mirror image is in behind the mirror. That's why when you're looking through it, you see the image inside of it, right? And they are small in size, so we can catch the larger area here. So that's very important. So if you use a other image like concave one, then it is different. You will see a larger images, big in size. Maybe you have seen a concave mirror. When you're looking through it, you see like a big base in there. All right, so this is just, I listed it as a question, but it's not really a question. So here, let's say you want to look at your full body through a mirror. What size of mirror do you need? Do we need a same size mirror as ourselves or something else? Actually, we need only a half your height mirror. So if you're 6 feet high, then you need only 3 feet high mirror to see your whole body. You don't need 6 feet high mirror to see yourself. It's from the light rays that you can see these light rays that's coming into our eye from the body, like all the way bottom, like from your feet, the light rays hits the surface of the mirror and then it's get reflected. But if you extend this light, it can extend it and it can create the image over there. So to see ourselves fully from a mirror, we need only half our half height of ourselves size mirror. All right, so the other thing is refraction. Have you ever seen this type of images? Like when you have a straw in your cup, you will see like it's bended, right? So like this one. When you put a spoon or a straw, you will see like it's bended here. It's really not cut off, but it's bended, right? And also maybe you have seen this type of pictures if you're a nature observer. So here you see like two images, right? So one of these is due to the reflection, other one is the refraction. So refraction is different than reflection. So refraction happened when the light enter into a different medium. So when the light enter to a different medium, it's bends. Like if you send a light in this picture, this is a second medium and this is the first medium. So when the light enter in there, it's get travel if it hits the perpendicular to it. But if you send something like angle to the surface, then it will reflect differently. Now here, I'm going to take you to a, as I cannot do the demonstration, I'm going to use the simulator. Sorry about that. That's what we are surviving these days on. The simulators. Okay, here we go. Where's my simulator? Okay, here you go. Here, this is this protractor that we can measure the angles. Okay, and here this is the light device. It's a laser light, red laser light. So in the class, you would have used the real laser light and reflect into a surface and see like what's going on. So let's say this medium is air, right? The first medium over here where the light beam is producing is in the air. And let's say the second medium, I'm going to use, let's say glass. So I'm going to use glass here and send some light beam. So here I'm sending a light beam. Okay. So when I send the light beam here, the light, let's say I'm inciding it with the 60-degree angle. Okay, so here light comes in the 60 degree. So it's from 0 to 60. I'm not measuring it from the surface, but I'm measuring it from this perpendicular line here. So this is 60 degree. And then the light hits there and there are two pieces to the light, right? Here, one portion is going up here and it's go again in the 60-degree mark, right? So this angle is 60 degree. So incident angle is equal to the reflected angle here. So these two angles are equal. That's the reflection. Now this one that's enter into the water, it's going into the second medium. So this has happened due to the differences in the medium. So here's the first medium and this is the second medium. I make the second medium as glass. Sorry, not water, it's glass. So the light is entering into the glass, right? Now here, this angle is not 60 degree. It is a different angle, right? So this angle called the refraction angle. Refraction angle is not equal to the incident angle. So it's another thing. Anyway, so when the light enter or hit onto a surface of a different medium, then the light get reflected. So reflection is in the same side as the incident beam. And the other ray that's enter into the second medium, that is the refraction. So whenever you see, like when you put a straw into your water cup, you see it's bended, right? So that's due to this one, the refraction. Reflection, that's how the mirrors create images. Refraction is different. So now let's use a different material. So water or air. Let's use air. See, if it is air, there's no medium change, like there's no mirror or a lens, so the light goes straight. But when I enter a different medium like water, it's do reflection and refraction. Okay. And when we are using a different shape, like this one. Okay. Now I'm going to send a red beam. See, like here, it's facing a one medium difference from air to glass. So the light bended. And again, when it's entering to this surface, it's from glass to air. So it's bending again. So we can bend lights using these different shapes. Now let's use a different one, different shape. So let's say I'm using this one. See, like I can change the bending by using different devices. Now I can combine things around and bend it differently, right? So when we have nearsightedness or farsightedness, we are using different shapes of lenses to bend these lights. Right, so I'm taking you back to my PowerPoint slide. It's 10:15, okay. All right, so the reason for reflection is the light travels in different speeds in different materials. Okay, so here, take you back to my PowerPoint slide here. So the speed of light in glass or water is less than that the speed of light in air. So when the light rays enter into a second medium, it slows down if it is a denser material than the initial material. So the wavelength will be changing. Sorry, the wavelength has to be the same. So the it's changing its speed to change the to react to the second material. So he basically, each material has its own index of refraction. So index of refraction is the ratio between the light speed, the speed of light in the vacuum, which is C, and divided by the speed of light in that particular medium. So if you're using water, the light speed in the water and the light speed of the vacuum. So you take the ratio between these two to calculate the refractive index. So refractive index are different for each material. Here's the list of refractive index for materials. So vacuum, the index of refraction is 1. For air, it's about 1. For water, it's 1.3. For glass, it's about 1.5. Look at this, it's diamond. Diamond is 2.417. So that's something make it more expensive, right? You know, diamond is pricey because of this. Its refractive index is higher. So when the light enter into the diamond, it's get reflected inside without coming out. So we see this nice, colorful, bright shining of the diamond. So diamond is pricey because in that index of refraction is high. Now we have this artificial diamond these days because people know how to create this high refractive index materials. So this, when the light reflect, it's follow another theory. So remember, like this reflection angle and the index angle, incident angle is not the same. It's follow a different rule, which is, this is for small angles. It's the refractive index times the incident angle is equal to the refractive index times the reflection angle. Actually, there's a sign of function in there, but for small angles, we can rule this out. So N1 theta 1, that's N1 means the refractive index of the first medium, and theta 1 is the incident angle, and N2 means the refractive index of the second material times the refraction angle over here. So basically for air, N1 will be 1. And if it is entering to water, it will be 1.33. So you can use these numbers to calculate this reflection angle. Then when the light enter into these different shapes, light getting, what do you say, like it's making these 7 colors, right? So you can disperse these colors into 7 colors. So we are using the word dispersion to say that the light get distributed, like making 7 colors. I don't know, I don't get that. So when the light enter into a glass prism like this, then the light waves bended, but here the blue color and the red color, the bending angles are different. So it's depend on their wavelength. So, you know, like white light is consist of 7 colors and it's come from different wavelengths. So depending on wavelength, their speeds are different. So the different wavelengths are bending different amounts. So basically, the blue light is bent the most than the red light. So when it's entering into a different material like glass, the light rays are bending differently depending on their wavelength. So that's why we see these 7 colors separated when it's traveled through a prism. So Newton noticed that for the first time. This is a real experiment picture that when the light rays enter into the prism, it's create these 7 colors. Okay, so if you're in the real class, we would have do these nice demonstrations. So we call this as the dispersion, like creating 7 colors by bending these lights. That's the reason we are seeing rainbows. Remember, like we don't see rainbows at every time, at every day. We see rainbows when there's a rain coming up or just after the rain, right? So there should be water molecules in the air. When the water molecules is present in the air, we see these rainbows. So basically when the sunlight enter into the water, this is a water bubble, and you know, like water is just a film. Around here inside we have air, but outside it is just a water film, right? So there's a water film over here. So when the sunlight enter in there, there's a surface difference. So outside is air, but this is a water bubble. So water will get disperse the sunlight due to the refraction. So due to refraction, the sunlight will disperse, and again it hits the other surface of the water bubble, and then again it will get reflected because it's entering into a same medium. Inside it's water, right? So here the sunlight enter into the water molecule, so it is refraction because it's entering into a second medium. Here it hits on the water surface and it's get bended backward again to the same side of the water, so it is reflection. And when it's entering into this surface, it's again coming back to the air surface, so that means the light get refracted. So here refraction, then comes the reflection, then refraction. Due to this bending of light, we see the 7 colors of the rainbow. Isn't that interesting? Like you can see this rainbows due to this water molecule. So water molecules did a big job bending this light, and the white light consists of 7 colors. So the 7 colors will bend in different angles from we call this as the refraction. And then in the other surface, it's reflecting like a mirror. And then again, it's like a refraction again, because it's entering into a different medium and it's dispersed the 7 colors out. Okay, it's 10:20. So let me take your attendance. It will take about 5 minutes, and then I'll continue on lenses and how the lenses can be used to for different applications. Maybe I'll quickly go over this one because I need about 10 more minutes on this slides. Yeah, before I go to the top part, I'll use 10 more minutes and let's look at what other lenses are. Then I'll go to the top part. All right, so lenses, this is different from mirrors. Remember, like mirrors, it is just a concave or convex. It's mirrors because it's just, there's no thickness into that. When the sun or the light rays comes in, it's get reflected. Now lenses are different. Lenses made out of different materials like glass or plastic. There are different materials that we are using to create the lenses, and the lenses are coming in different shapes. So this one is a biconvex. So both sides are convex. It's bended like outside, right? So look at this shape. It is a convex, and it's biconvex because both sides are convex. Then this one is a planar convex. This side is convex, but this side is just a plane, straight line, right? So this is a planar convex. This is a convex and concave. See the shapes? So one side is caved, other one is vex. So it's a convex and concave. Then all the way down here, it is biconcave. So here the two sides are caved inside. So both sides are biconcave. So likewise, different shapes. We can create different shapes of lenses, and depending on their total result, like what is happening to the light, they behave like a converging lens or a diverging lens. Let's look at what is converging and diverging means in light. So lenses are curved mirrors, I would say, but inside there's a different material. So it's a filled curved mirrors, lenses, right? So it can focus lights. It can focus or diverge lights. Okay, so let's look at this one. This is a shape. This shape, it's convex. Okay. So this is a convex lens, this shape, and this one is a concave lens. It's a concave, biconcave and biconvex. So here, if you observe these light rays, these 3 light rays are parallel to each other. When it's enter into the convex lens, it's get collected into one point. So we call this as a positive lens because it's going in the same direction as the sun, the light rays travel. So light rays comes in this direction and it's bended into the same direction. It's going towards right direction, right? So these are convex lenses, and it's converging, and it is a positive lens. The focal point is in this side, and if you measure the distance from the center of the lens to this focal point, we call this as the focal length. And on this one, it is different. It's a convex lens. Did I mix up? It's a concave, right? This is concave lens. So when the light rays hits on the surface, it's get diverge. It's distributed around. So this is a diverging. And if you extend these lines, these gray color lines are the extension of the real beam. So it's connecting somewhere here, right? So it is in the same direction where the light rays comes initially. So this has a negative focal length. So we call this as negative lenses. So if you are using glasses, if you're using any type of eye aids, if you look at your prescription, you will see whether you have a positive focal length or a negative focal length. So depending on which type of lens you're using in front of your eye, you will see that it is a positive or negative. So if you're using this type of one, then it is a positive lens. Now I have a magnifying glass luckily here. So if I touch this, I can feel it. I feel like it's popped up outside. So this is this shape. When I touch it, I feel it. It's going this way. And also you can, by looking at it, you can see whether it is a diverging or converging, because magnifying glass make the things looks bigger. The shape is this one. It's a converging lens, and it is a positive lens. All right, so sunlight. So the focal point is somewhere here. So when you're using this type of lens, it's a converging lens. It's collect all the light. So you can have it over here. So solar cooking, we are using this. When you're little, if you watch this Toy Story movie, I think Toy Story 2 or something. So there's two characters like Buzz and Woody. So they're using their head like a circular, like a spherical shape. So when they're outside, it burns their heads by lights bent through the shape of the lens. So if you're familiar with that, you can remember it. So the sunlight collected from this lens, and it's collected into one point. So this is a focal point, and you can use that energy to cooking or anything else, like making a fire. Then if you're using this type of lens, it's like a flashlight, right? So it's get distributed around. So it's diverging. It spreads the light out. Here's this slide show you like what is the focal point. So when the light rays are parallel to each other, it's connected into one point. We call this as the focal point. If you keep it like angled, again, they're collecting into one point in anywhere on the focal plane. So we call this as the focal plane. Sun rays are collecting into the focal plane. Okay, let's look at this application. So how do we see things in our eye? If you look at your eye closely, there's an eye lens, and it is in this shape, right? So which type of lens is that? It is a convex lens, right? So it is a diverging lens. It's a convex lens. And when we are looking at the things like outside or somewhere, the light rays that's coming from that object will enter into the eye. This is the eye lens, and the eye lens will collect these light and focus into the retina. Retina, that's behind your eye. So it's collected it there, and the optical nerves are running around here. So the optical nerve will catch that image, and it tells us to read the image. So any image that you see, this is what it does. And also our eye is really a special thing. It can control the size of this lens. It can change the focal length of the lens. It can shrink or stretch out. So you can catch more light when you are in outside, like let's say you are in the dark places, then I need it to be bigger and collect more light. Maybe if you have a pet cat, maybe you have seen their eye lenses. That's, you can see it clearly because their eye lenses are yellow in color and outside is bright black. So you can see their eye lenses really closely. So in the night time, their eye lenses are really long and thin because they're trying to catch more light into their eye. So they're making their focal length bigger. Likewise, we human, there's a limit, but we can do that as well. So when we're getting older, these muscles are getting dried up, and we lose that control. So that's why we are wearing glasses when we're getting old, like passing 40 years, then we have a little bit trouble controlling these eye lens sizes. And also then when you're using computers, it's always dry up our eye. So that's why it's recommended to use the eye drops to make it wet and keep it hydrated. So most of the common errors in our eye happens due to this impossibility of controlling this lens. So light is focused by the cornea and lens into the retina. The retina is made out of light sensitive cells called rods and cones. So these three types of cones are sensitive to light in different parts of the spectrum. So there's only three types of cones that can catch different spectrums, and it's create the colors as well. Now here, so most common visual problem of people who do a lot of reading is nearsightedness. Again, when you're getting older, we get this nearsightedness as well. So for me, I have the nearsightedness. I'm wearing glasses. As it's online, I'm not using it because it's hard. But if I'm driving, I need my glasses to see the far distances. So I'm nearsighted because I can only see near side things easily. So what's happening in my eye is when the light enter into there, it is not collecting the images back in the retina, but it's collected somewhere in the front. So I need some assistant that I can push this image all the way back to the retina. I'm not fully blind, but I see the image, but it's not sharp as you do. Young people can see it clearly and nicely unless you're having any other issues. So in a healthy eye, usually these light rays are collecting into the retina back over here. But if you are suffering from nearsightedness, the light rays are connecting somewhere here in front of the retina, so we can see it. So we are using this shape of lens, the diverging lens, to send these lights all the way back. So it's like we kind of pushing this image back into the retina so we can see it clearly. Every 2 years, I have to check my eyes and make sure that I'm good with this size of the lens in my glass, because over the years, our eyes are changing, our muscles in the eye lens are drying up. So we have to change it. So if you're using glasses, you have to check your eyes like every 2 years as is prescribed. So on the prescription, if you are using glasses, you can read your prescription and it will tell you the size of the lens that you're using here. It might be positive or negative. They don't use the convergent or divergent words, but they use positive, negative signs to say that. So this is nearsightedness. You can imagine like what happened with the farsightedness then, right? Again, here, this is the normal eye. So the light rays are collecting in the retina that you can see it clearly. But if you're nearsighted, light rays are not pushing all the way back to the light, the focal point. Light rays are traveling, but the focal point is somewhere here. So I can see it sharp images. Then in the farsightedness, the light rays are collecting like back in the retina. So again, you see a blurred image, but not a sharp one because it's collecting all the way back in the retina. Now we need to fix that, right? So in the myopia, so that's the nearsightedness. So you're using the concave lens in front of the eye lens in our glasses, and I can shift the mirror, the image of the object into the retina, and my nerves can read it really easily and sharply. Then in the farsightedness, the light rays are collecting back in the retina. So we need to bring it back into the retina to see clearly. So we are using a, I think you can see this picture. I'm not sure, it is not that sharp. It is a convex lens, like a magnifying glass. So we are using a magnifying glass shape glass over here. Now, those people who are using this type of glasses, those who are suffering farsightedness using magnifying type lenses in front of their eye. So when you see those people, like when you're looking from outside, you will see a magnified picture. I don't know whether you can see my eye. So if I keep it like in front of my eye, you will see a magnified eye of myself from yourself. Like when you're seeing my eye, it's magnified. Do you see that? Like if you are watching my video, you may see my eye. This is my normal eye, but if I have a magnifying glass in front of me, I think you're seeing all my surroundings, maybe. I don't know. So, okay, here, my nose, it's much bigger, right? So that's coming from this magnifying effect. So if someone is using a farsightedness correction, then we can see it. We can notice by looking at the lenses. Okay, so these slides are available on the canvas. Please have a look, and I will be opening another homework tomorrow.
The last picture is not in the slides.
Okay, I will update that then.
Okay. Thank you.
Anytime like I update, I upload the PowerPoint slide, then before the class I review my materials and I feel like, oh, let's add another picture. So I keep adding things. But after the class, I always update the version there. I did the same thing last time. So if you printed out or downloaded the PowerPoint slide, make sure you download it again, like after the class. Okay, so let's take your attendance and maybe 2 questions on top of that. Okay, I think you can see the attendance code, so please send that. And then let's try a problem. So I keep it open. So if you need more time, you may still send the attendance code. If you are done sending the attendance code, you may start answering this question. What happened?
Did you remove the question?
That's what I'm trying to figure it out. Okay, I reopened it. Can you see it now?
Yes, we can.
Yes, I see you are responding. Okay. Also, I still have this attendance code open, so you should be able to send your attendance. All right. Okay, so I'll close the attendance code. I think almost all of you got it. 103. Still, I'm missing one of you. Okay, so I'll finish counting the attendance. I'm sorry. Okay, sorry for the noise. So answer is reflect. It's a mirror, so the light rays reflect. All right, next question. So it's not refraction. Mirrors do reflection. Lenses do refraction. Diffusion is a different thing. It's again refraction, but it's talking about how the 7 colors get reflected. Okay, next one. Okay, now this girl is wearing a glass that makes her eyes looks larger than actually they are. So what are those glass type? Are they concave, convex lenses or concave, convex mirrors? Okay, I'm going to close this then quickly. Okay, now you're responding really quickly. Nice. Here you go. All right, let's look at your responses. Okay, I know you need a little bit time to understand like what it is. It is convex or concave. All right, so I'm glad that almost all of you know that it is a lens, not a mirror, right? Okay, so if you're saying mirror, it's not, because through mirrors, you cannot see other side. You can see only your side, right? So mirrors doesn't do this. So, and also in an eyewear, you cannot find mirrors. You're always using lenses, right? So those who answers mirrors, you are not with me. You need to read again the slides and work on it. All right, so lenses, that's correct. Now, is it concave or convex? I think those who answered maybe get confused like between the words, because I always get confused as well. So convex lenses are the magnifying lenses. So this is a magnifying glass. It's a convex lens. So when you look at her eye, it's magnified, right? So that means you're looking at someone else's eye and it seems like it's magnified. Then it is a magnifying glass, which is a convex lens. So the correct answer is B. If it is a concave lens, then you will see her eye get small than its usual. Okay, anyway, I'll open the homework so you can practice more. All right, so it's 10:40. Now, if you go to your Canvas page for the class, I don't know whether I have it here. No, I don't have it. Under the lectures, I add another PowerPoint slide with dual nature of light. It has a couple of slides. So before you do homework, please read that. I will go over that topic in the next class, but you might need those to answer a couple of homeworks. All right, so please use both PowerPoint slides, the one that I used today and also the other one. It's a very short one. I named it as the dual nature of light. So please read that before you do the homework. Okay, all right, so I'll call this as the end of the week, I guess. It's Thursday, right? So have a good weekend and please work on homework. I'll open it most probably. Okay, so if you have any questions, please stay in the meeting. Otherwise, you're good to go.
Thank you.
Thank you. Bye.
Bye.
I have a question.
Yes, go ahead.
Did you say that we're using the lockdown browser for the next exam?
Yes.